Figure 20.4, type defs found in first-class containers. Now, when you're working with templates in general, the declarations that you create can actually become quite complex. And for that reason, the designers of the standard template library came up with some common type def names to represent very complex types underneath the hood of these various container classes that we'll be working with in this lesson. Now, in this table on the left-hand column, you can see those common type names. So anytime you ever come across allocator type, it's going to represent the type of the object that's used to allocate the container's memory. And it turns out that there's very complex objects working behind the scenes to maintain the memory for our standard template library data structures and to maintain that memory in a very efficient manner. So one of the goals of the standard template library is to create extremely high performance data structures, and for that purpose, rather than just using the standard new and delete operators, they actually created their own customized new and delete operators to help manage the memory in the most efficient way possible. Now, another common type def is the value type def, and that represents whatever type of element is stored in the container. So, for example, if I say I want a vector of integers, the value type def would actually represent int in that case, whereas if I said I wanted a vector of employees, value type would represent employee in that case. The reference type def simply represents a reference to the type of element that's stored in the container. So again, if I had a vector of employees, then the type def reference would in that case represent a reference to an object of type employee. We also have const underscore reference, which represents the same thing as reference, but where it's a constant reference, meaning that you can only look at the data, you cannot modify the data. And similarly to reference and const reference, we have pointer and const pointer, and of course these are pointers rather than references. And then we have also iterators and const iterators. An iterator is going to be a pointer-like item that allows us to walk through the container one element at a time, and we can either look at the data or potentially modify the data using that iterator, whereas a const iterator allows you to do the same thing in terms of walking through the collection, the container, but only looking at the data, only reading the data. And as we continue this table, we have several other type defs. Reverse iterator and const reverse iterator allow you to get iterators that walk backwards through the contents of a collection. And again, we have the difference between the non-constant and constant versions. Of course, the const version does not allow you to modify the data. Then we have a concept called the difference type, and this is the result of subtracting two iterators that are referring to the same container. Now, normally when you subtract two pointers into an array, it gives you the number of items between the two pointers, and there's a similar concept when dealing with iterators that are pointing at a container. And then finally, we have the size type, which is a type def that just represents the data type that's used for counting the items in a container and indexing through the elements of a container as well. So this, you may remember the size of operator and the fact that it returns type size underscore t, which basically is just an unsigned integral type that allows us to write more portable programs, and the same concept applies here with size type as well. For the most part, when you're writing your code, you probably won't need the size type constant all that frequently, but if you ever get to a point where you need to represent the size of a given container rather than declaring it to be of type int, you would declare it to be of type size type, and the reason for that is that it's implemented in a way that can be portable across different platforms.